The Omega Navigation System is a worldwide all-weather navigational system providing a fixed accuracy of 1 to 2 nautical miles, which can be used by submarines and the aircraft as well as surface ships. Like Loran, it's a radio navigation system. However, Omega uses VLF, very low-frequency radio signals, which permit extremely long-range navigation, consequently reducing the number of stations required to provide a worldwide navigation system. Another important feature of the Omega system is the simplicity of its equipment, which makes it very easy to operate and maintain once you understand a few fundamentals. To provide worldwide coverage, the Omega system will use 8 VLF transmitting stations. 1 in Norway, another in Trinidad, 1 in Hawaii, and another in north-central United States. Of the remaining, 1 is in the Indian Ocean, another in the southern part of South America, 1 in the Tasman Sea area, and finally, 1 in the western Pacific. The actual spatial relationship of these stations to each other may be better understood by viewing them on this globe. The stations are spaced so that any position on the globe will receive usable signals from at least 5 stations. Each of the stations is assigned a letter designation, A through H, and each transmits continuous wave VLF signals in the 10 to 14 kilohertz band. The signal format is transmitted once every 10 seconds, with each station transmitting in turn for approximately 1 second, and with all transmissions synchronized to a common standard time. Actually, there's a very slight difference in the duration of each station's transmission. For example, Station A transmits 10.2 kilohertz for 9/10 of a second, Station B for 1.0 seconds, Station C for 1.1 seconds, Station D for 1.2 seconds. The same transmission periods are repeated for the other 4 stations and simply rearranged in order. There is a 2/10 second separation between signals. The difference in transmission duration and position can be used to identify the different stations. However, since the closest stations will usually have the strongest signal, they are identified by their signal strength. But no matter what method of identification is used, the important point to remember at this stage is that the transmitters are sending out signals in a time-shared sequence, and that every Omega receiver is picking up signals from a number of transmitters. These receivers are not only receiving the signals, but they're also comparing them to determine the phase difference between them. To explain phase difference, we'll use sine waves to represent the signals being received. As long as these waves coincide, we can say that they're in phase, or that they have a 0 phase difference. But as the relationship between the waves begins to change, a phase difference begins to appear. Now, let's visualize the relationship between a receiver and 2 stations, with a baseline drawn between the 2 stations. At a point midway between the stations, there's no because they have traveled the same distance. And as long as the receiver remains on a line equidistant from both stations, the phase difference remains 0. This series of 0 phase points establishes a line of position for the receiver. As the receiver begins moving toward one station and away from the other, we begin to get a phase difference due to the difference in distance the signals travel. In our simplified receiver, you can see this phase difference being measured. The sine waves simply show the changing phase difference graphically. As the receiver moves away from the midway line of position, also called a 0 phase contour line, the phase difference gradually increases from 0 through 360 degrees or back to 0, thus locating another 0 phase contour line. Now, if we were to draw a new line of position at each 0 phase difference interval, we would get a series of 0 phase contour lines dividing the area between the 2 stations into lanes. These 0 phase lines appear at half wavelength intervals, And so, for 10.2 kilohertz, which is the basic frequency of the Omega system, this gives us lanes that are 8 miles wide near the baseline between stations. For all practical purposes, the lines are parallel near the baseline, even though they are hyperbolic and actually diverge as they move away from the baseline. The distance between the stations is so great, however, the divergence seldom becomes significant. For identification purposes, the lanes between each pair of stations are numbered. This is done by assigning the number 900 to the midway or zero contour line between the two stations. On one side of this line, moving toward station A, the lines are numbered in decreasing order. On the other side of the 900 line, moving toward station B, the line numbers increase. The same arrangement is followed in numbering the lanes between any pair of stations, with the numbers always increasing from the lower to the higher letters. In the Omega system, these lane numbers are always used to determine the ship's line of position, and these are the numbers that the lane counters of the Omega receiver use to identify a particular lane. On this AN-SRN-12 receiver, the lane count is indicated by the 3 digits in the window at the left. Omega receivers also give a percent of lane reading, which permits an LOP to be established within a lane with greater accuracy. Percent of lane is obtained by treating each lane as though it were divided into 100 equal parts. For practical purposes, the percent of lane measurement is used as the measure of phase difference. On the SRN-12, percent of lane is indicated by the 2 digits on the right. The network of 8 stations provides a grid of lanes covering the entire globe, and this gives the geographical references we need to be able to fix our position. The signals from one pair of stations will give one LOP. Using a third station gives another pair, and consequently, another LOP. And at the point where these two lines intersect, we get the fix. Now, although the areas between stations are divided into lanes, which are numbered, the receiver still can't identify any particular lane without some help. By means of phase difference, it can measure its location within a lane and count the number of lanes that it crosses, but it cannot identify the actual number of the lane, and this results in what is called lane ambiguity. This ambiguity is resolved by initializing or setting the receiver to the correct lane when it is originally turned on. This is easy to do at the beginning of a voyage when a ship is generally at a location where its position can be accurately established. An Omega chart also gives the lanes in which the position is fixed, and with this information, we can initialize the receiver. The lane counters are set to the lane numbers taken from the chart. There's no need to adjust the percent of lane indicator because this sets itself automatically. Once the counters have been correctly set, the lane count continues automatically, with the numbers of the counters continuously indicating the position of the ship as it moves across the different lanes indicated on the charts. This, then, is the way the Omega receiver works. Once it has been initialized and the station pairs have been selected, the navigator takes his lane readings, first from one pair of stations and then the other pair. This gives him a line of position for each pair of stations, and at the point where the LOPs intersect, he can fix his position with an accuracy of 1 or 2 miles. Of course, if a transmission is interrupted or the receiver fails, the lane count must be reestablished before the Omega system can be used again. For this reason, the navigator should always maintain a good dead reckoning track, which will assist him in lane identification. In order to reinitialize the receiver after a loss of lane count, the ship's position must be known within a half lane width, which, using the 10.2 kilohertz signal, would be plus or minus 4 nautical miles. Obviously, the whole problem of determining which lane the ship is in could be greatly simplified by making the lanes wider. Since lane width is a function of frequency, we can get the additional area simply by changing the frequency. This is precisely the way the Omega system resolves lane ambiguity, by having the stations transmit at frequencies of 13.6 kilohertz and 11 1/3 kilohertz, as well as their basic frequency of 10.2 kilohertz. The additional frequencies are transmitted during the same time interval of 10 seconds, but the format is arranged so that no two stations are transmitting on the same frequency simultaneously. These particular frequencies were selected because of the relationship between them. For example, the frequency 13.6 kilohertz yields a lane width of 6 miles, so that 4 13.6 kilohertz lanes equal exactly 3 of the 8-mile 10.2 kilohertz lanes. By itself, the 13.6 kilohertz transmission doesn't help resolve ambiguities because it produces smaller lanes. In order to increase lane width, we need a lower frequency, which we obtain by having the receiver electronically take the difference between the 10.2 and the 13.6 signals, giving us a much lower frequency of 3.4 kilohertz and a lane width of 24 miles. This new lane helps resolve lane ambiguity because now we have a lane 3 times as large in which to place ourselves. And instead of being required to know our position within plus or minus 4 nautical miles, we now have a radius of 12 miles in which to establish lane count. Here's the way it works. By dead reckoning or other navigational means, we can establish our rough position within one of the 24-mile lanes. Then, a percent of lane reading immediately tells us in which part of the large lane the ship is located. Since the 24-mile lane corresponds to 3 8-mile lanes, knowing the percent of lane enables us to place the ship in one of the 8-mile lanes, and we can reset or reinitialize the receiver accordingly and resume automatic tracking. Using the same procedure with the 11 1/3 kilohertz signal and the 10.2 kilohertz signal, we get a difference of 1.1 1/3 kilohertz with still wider lanes of 72 miles, which in turn give us a much larger margin for ambiguity. And using the same procedure, we can work our way down to a 24-mile lane and ultimately to an 8-mile lane. In spite of the availability of the other two frequencies, the 10.2 kilohertz signal is the essential frequency needed for accurate navigation. The additional signals simply make it possible for suitably equipped receivers, with the aid of dead reckoning, to resolve lane ambiguity anytime and anywhere on the globe. After the receiver readings have been taken, the Omega Skywave correction tables must be used to take into account changes in the ionosphere at different locations, different times of the month and day, and the effect these conditions have on transmission. A geographical index gives the pages which apply to the different locations. And in the tables under the date and the hour, we find the amount that must be added to or subtracted from the percent of lane readings. This may also change the lane count readings. Briefly reviewing the basic features of the Omega navigation system, we begin with 8 VLF transmitting stations strategically located around the globe. The stations transmit on a time-shared basis, with their signals phase-locked to a common standard time. The signals divide the area between station pairs into lanes of equal width, and the lanes are further divided into 100 equal segments, which appear on the receiver as percent of lane. The lanes for the 10.2 kilohertz signal are 8 miles wide, The lane for the 3.4 kilohertz signal is 24 miles wide, and the width of the lane for the 1.1 1/3 kilohertz signals is 72 miles. The Omega receiver is started and time synchronized with the transmitters at the beginning of a voyage. At the same time, the station pairs are selected, and after consulting the skywave correction tables, the lane counters are set. From then on, the lane counting is automatic. The navigator simply takes his receiver readings, uses the skywave correction tables to correct them, and at the point where the intersecting lines of position cross, he obtains his fix quickly and easily. When this speed and ease are added to the other advantages of the system, such as the worldwide all-weather coverage, dependability and accuracy, simplicity of operation and maintenance, it's easy to see that in Omega, we not only have a very practical system, but also one that represents a milestone in the art of navigation.